Okay, so today we start talking about some really interesting stuff. Today we move off chip. Up until now, everything we've done has been on the breadboard, right? And been on the development board. Now we start talking about how to talk to other things. There's two main communication protocols we're going to talk about, SPI and I2C. Today and next class, we're really going to be talking about SPI and how it relates to your final lab. Yay, final lab of the semester. But you're going to be using this again. I guarantee it. There are other courses that you're going to be using this processor in, and you're going to need to know this stuff. So let's start with the background of the serial peripheral interface. The serial peripheral interface is nothing more than a synchronous protocol, and its hardware is two shift registers. Same shift registers we talk about in digital logic. Bunch of flip-flops, outputs tied to the inputs. That's it. A bit of history. It was started by Motorola. Motorola now is free. Well, Motorola spun off that division into something called Freescale, and then I think Freescale was bought again by Motorola. Don't quote me on that last part, but it has. Sometimes you'll see it called a 3-wire interface, sometimes a 4-wire interface, depending on who's telling you what. There are basically 4 things that you need. You need 2 data lines, okay? They go in opposite directions, so they're directional data lines. This isn't like UART. Well, I guess it's a little bit like UART. But the third line is a clock. And this clock is generated by one of the 2 devices that is talking. Right? So actually, up till now, it actually looks similar to UART because we've got a transmit line, a receive line, but now we've got a clock. Yes?
Is that a system clock or is that a separate?
Separate clock. So we'll get there. There's a clock generator that does some stuff. Okay, so just like most of the peripherals, we can kind of set the frequency we want to talk at. The difference here is typically SPI will run in the megahertz as opposed to UART, which is like a couple thousand hertz or a couple 100,000 hertz. This is in the megahertz. The last little lonely line down here is a indicator of who you want to talk to, and this is where SPI is really powerful. If you wanted to use UART to talk to something, you need 2 lines, a transmit and a receive. If you wanted to talk to somebody else, you would need another transmit and another receive. So if you wanted to talk to n devices, you would need 2 to the n lines. The way that SPI works is most of the lines are shared in common. So the common lines are MISO, MOSI, and S-clock. And that's how you pronounce them. MISO, MOSI, S-clock. MISO is a mnemonic. It stands for master in, slave out. Anybody want to guess what MOSI stands for?
Master out, slave in.
Ta-da! You have just intuited. So that's all there is. The nice thing about this is it's self-descriptive. It doesn't matter how you're hooking up. You automatically know that MISO connects to MISO on all the devices, because this is going to be on this guy. This is an input, master in. He's the master. You can tell because he's green and it says master. Master in, slave. So this is an input. On all of the slave devices, master in, slave out. These are the outputs. So the inputs automatically connect to the outputs. Everything is fine and dandy. S-clock is in parallel, MISO, MOSI in parallel. The only thing that is not in parallel is each slave device has its own slave select or chip select. Depending on who's making the part, they'll call it something slightly different. It's basically an enable. It says, I want to talk to you up top, I want to talk to you down below. So for n devices, you need your 3 common lines plus n chip selects. Okay, so for 2 devices, you need a total of 5 pins. To add another device, you just need 1 more pin. You can actually get away with even less pins. If you wanted to talk to 8 devices, it's possible to do it using only 6 lines. How would you deal with 8 devices? If you had 8 things on the output, how would you control it with only, well, 6 minus 3 is 3. How would you control 8 lines with 3 lines? On the right track, but a MUX has 1 output, not 8 outputs. decoder, right? If you use a couple of lines on your master device to feed a decoder, you can then connect the outputs of that decoder to many more lines. So there's lots of ways to talk to a lot of devices with relatively few lines. And on microcontrollers, especially small pin count microcontrollers, that's a real interesting thing. You can even do really crazy things, like you can have one SPI device that you talk to, and it has a bunch of outputs, and then you tell it to do something, and then you talk to SPI again, but now that first SPI device is told the second level of SPI. Anyway, MISO, MOSI, S-clock. All that's happening here is we have two shift registers. As this guy clocks bits out of this shift register, they appear in this shift register. And at the same time, whatever's in this slave device is actually getting clocked in. It forms a circular loop. Okay. So the thing about this circular loop, it means that both reading and writing happens at the same time. So it's a little different from our full duplex communication of the UART. With a UART, you could send some bytes whenever you wanted to, and the other guy could send bytes to you whenever it wanted. This happens at the same time. What's the song? Strangers in the Night? Passing? No. Whatever. It happens at the same time. If you send a single byte out, you're going to receive a byte at the same time. So how do we hook this thing up? Well, on the ATmega 32, on port B, there are 4 pins labeled S-clock, MISO, MOSI, slave select bar. One of the things about SPI that you'll find is most of your chip selects or slave selects are active low. So when you're trying to talk to something, you actually bring a line low. That enables the device. You talk to it for a while, and when you're done, you have to remember to bring it high again. Yes?
Is there a reason for that?
There's probably a physical or cost reason in the silicon why it's done that way. And that's sort of like a 260 topic, right? The reason now probably is because that's how it's always been done. And so to be compatible with lots of devices, we do it that way. But when we started, there was a reason. What that reason was, I can't tell you right off the top of my head. So the 328P also on port B has slave select, MOSI, MISO, and S-clock. The difference here, all right, I want you to notice that it's B2, B3, B4, B5. On this one, it's B4, B5, B6, B7. So it's something to keep in mind as we start talking about code a little later on in the lecture. Different chips, even in the same family, can have slightly different pinouts. Okay? But the names are the same. MISO, MOSI, S-clock, and slave select. Okay, in terms of software, this is one of the simpler peripherals we're going to talk about. Here's our status register. It's relatively sparse. There's only 3 bits. Okay? First is the SPIF bit, which I referenced moons ago, many moons ago at the beginning. I said, oh, we could look at the SPIF bit. Well, now you know what the SPIF bit means. It's the SPI interrupt flag. Flag, not mask. This is going to be set when an SPI interrupt occurs. We have a write collision flag, which just means something happened. We overwrote some data. It's an error condition. And finally, we have one control bit, double speed. Okay? It's for those really interesting parts in songs where you up the tempo. If you put a 1 in there, it means the SPI is going to run twice as fast. This is the control register, and it has some things that you'd expect, like an SPI enable. It's going to turn the device on. SPI interrupt enable. I know because it says Internet Explorer at the end of it. Then we have a few configuration bits, and these deserve a little bit of time to go through what these are, and we're going to go a little out of order. We're going to start with clock and phase. So we've got master slave select, data order, clock and phase, and then the clock rate select. All right. Polarity and phase can be a difficult topic if you overthink it. Okay? If you just accept that it makes things work correctly, it's pretty easy to see based on just this diagram. All right? If we have a clock polarity of 0 or a clock polarity of 1, that says where we are, high or low. If you put the clock polarity at 1, the clock signal is exactly the opposite. Okay? Where clock polarity 0 has a high, clock polarity 1 is a low. That's it. Phase says where the data changes. I don't know if you can tell. Do you see that there are dashed lines and not dashed lines? Okay. When the phase is 0, the data is stable on dashed lines. When the data is when the phase is 1, it's stable, as in not changing, on the solid lines. So we've got dashed lines and solid lines. When you combine these two things, you must read when the data is stable. That's all it means. So if I choose phase 0, I'm either going to read on the falling edge of a clock polarity 1 or the rising edge of a clock polarity 0. That's all it means. Okay, we have to read when the data is stable, and we have to change when we're not reading. So here, with phase 1, we are stable on the dash, change on the solid. Now, why on earth would we need? Why don't we just always read on the rising edge? Because that seems fairly common, right? Read on the rising edge, change on the falling edge. And in fact, if you look at these, phase 0, 0, 0, reads on the rising edge, changes on the falling edge. And if you look at 1, 1, it reads on the rising edge, changes on the falling edge. They're actually the same for all intents and purposes here. The reason we have this configuration is because different peripherals didn't get the memo that we all do things the same way. So sometimes you have to adjust this. You might have to read on a falling edge, change your data on a rising edge. Yes?
Can you change these specific to the peripheral if you have multiple set up?
Yeah, you can modify it in between transmissions. I would try very hard at the design stage to avoid that kind of shenanigans. And the truth is, anything that's made recently, most anything that's made recently, is going to work in the 0 mode or the 3 mode. The SPI mode is just the decimal representation of polarity and phase together. So mode 0, 1, 2, 3. Most things you'll find these days are just 0, 0 because it's the way we think. But you may run into a legacy device that you need to deal with. So most of the time, we're just going to leave polarity and phase at 0. But we always have to check the data sheet of whatever peripheral we're going to talk to and look at its timing diagrams to see. And we're going to look at it. We're going to look for when does it expect the data to be stable? Does it expect it to be stable on the rising edge? Or does it expect it to be stable on the falling edge? And we can choose our clock phase and polarity based on that. So those are just 2 bits. Where are they? Polarity and phase, bits 2 and 3. Okay, next is the clock rate select bits. And actually, these clock rate select bits are also used in conjunction with that 2x bit from the previous register, the status register. Unlike the very fine-grained controls we have with UART, we don't have quite as fine a grain control here. It's very similar to the ADC, and then we have just a few dividers we can choose from. So we have, and it's not even a little bit out of order, 4, 16, 64, 128, 2, 8, 32, 64. The last set of 4 is just the first set of 4 divided by 2. Well, or sped up by 2, right? So the denominator is divided by 2, which is multiplying the speed by 2. So what that means is for our 16 megahertz signal, the fastest we can, or 16 megahertz clock source, we can do divide by 2. That's as fast as we can go. That's 8 megahertz is the fastest we can go. And by default, we do a divide by 4. So 16 divided by 4 is 4 megahertz. So when we talk to a device, it has a certain speed that it can talk at, a maximum speed. Yes?
It looks like 3 and I think 7 are both divided by 64. Is that the same frequency?
Yeah, so it's the math of it, right? So 128 divided by 2 is what? 64. So there's 2 ways to get 64. That's not a typo. That's what it is. Interesting catch. They could have done something a little bit cuter, but in this case, it's really not that big. So the slowest we could go is divide by 128, which in SPI land is like mind-numbingly slow. Okay, I'd prefer it if we could go right at 16 megahertz and divide by 1. That'd be awesome, but we can't. So that takes care of our phase and polarity, and our prescale. All right. The ones we didn't talk about, data order, just says which bit is going to go out first. So if I go back to that drawing of the two shift registers, which lives here, it's sending data out of this shift register, right? Now, the way we might think about this is it might send the least significant bit first. If we wrote a number out here, 1101, might send the 1, then the 0, then the 0, then the last one. That doesn't have to be the case. We might want to send the most significant bit first. It gives us the flexibility to choose whether we send the most significant bit or the least significant bit first. And why do we do that? Because not all peripherals talk the same way. So we're going to have to check the data sheet of whatever we're talking to find out. What do you want first? You want the good stuff, the little stuff? What do you need? I think that's the last one. Where am I? I'm right. Here, so that's phase, polarity, data order. The last is master and slave select. So this device, the 328P, can actually act as either a yellow device or a green device. It can be master or a slave. And in fact, it can swap back and forth between being them in the same firmware. It can go back and forth between being a slave, being a master. So when we are trying to talk to something, we want to make sure that we say, hey, we're going to be a master. That's what's going on with that bit. So the steps for programming this, before we go too much farther, I want to talk one more thing about the actual hardware itself. That SS pin, the slave select or the chip select pin, it's a little bit odd. You can set the direction of that pin to be an output, and the SPI is not going to control it. The peripheral doesn't control the slave select pin, which is a little odd. Why is it being included in all of these talks if it's not controlled by the peripheral? Well, again, it has to do with flexibility. It doesn't control it. You're going to have your firmware control the slave select pin. And we'll go over an example, hopefully, before the end of class. But if you set it to an input, because you don't have to use that slave select pin, as we saw in that diagram with two things. Obviously, these both can't be the slave select pin. So this one might be the slave select pin on the 328P, and this might be, I don't know, port B6, or it might be D0. Could be any I/O pin you choose. So you manually control this. In some larger AVR processors, they will have dedicated slave select pins that you can talk to more than one thing. It'll even, if you get like a UC3, which is a 32-bit processor line, it has two modes. It has 4 pins, so you can talk to 4 peripherals, right? But if you had a decoder and 4 pins, how many could you talk to? How many devices could you talk to? $16, yes, thank you. I know the lights are off, but you've got to be a little awake. Yeah, you can talk to 16. So the whatever it's called, ECE263 line actually has a mode where it will do a decoding for you. So instead of doing just a 1-hot output on those, it'll output a 0, a 1, a 2, don't do 2, 3, 4, 5, and so on and so forth. So you can talk to up to 16 devices. Be careful about that. So the slave select pin it seems like it's maybe not part of this peripheral so much. It's actually more important in the slave mode. When you want to make the 328P into a slave, that is the only pin that it will respond to. So where's my slave select pin slide? So when you are in slave mode, that pin is always an input. You can't control it through software. It stops being an I/O pin. And here's where things get tricky. Let's say you have a system, you've designed it, and instead of using the slave select pin, you decide that you're going to use port D5 as your slave select. Maybe because it was easier to route it on the circuit board, or whatever the reason, D5. So you're talking, you do all your testing, and and it's all working fine. And then suddenly one day you turn this thing on and it stops communicating. Well, that's odd, you say to yourself, and you start looking around and you say, oh, I never enabled this device to be a master mode, and that's why. So it's not working because it thinks it's a slave. So you go in manually into the debugger and you set the master mode bit, and then you hit run, and it's still not working. And you pause it and you look, and it's back to not being a master again. And you assume that your debugger is trash, so you throw it away. You get a new debugger, spend $100 on a new debugger, and it still doesn't work because it keeps saying that it's a slave. Well, it's because of this slave select pin. If it's an input and it detects a low going pulse, because remember, slave selects are active low, it automatically says, oh, screw this master mode business. Somebody's trying to talk to me. I'm going to enter into slave mode and I'm going to receive data. So as a rule, the first thing you talk to if you're a master mode device, use the slave select pin. Otherwise, it's just going to cause you problems, okay? If it's an input. If it's an output, you're kind of okay. Okay, so steps to programming this guy to get you up and running, sending bytes out. Got to make sure you're in master mode. Set the master mode bit to 1. Set your frequency. That requires 3 bits. Okay. The only limiting factor here is what your peripheral can talk to. Okay. There is no invalid choice here that will make the processor blow up. It only matters what your processor or what your peripheral that you're talking to off chip can handle. So if it can only handle, say, 2 megahertz SPI, megahertz, and you're running at 16 megahertz, you need to divide by at least 8 in order for the peripheral to successfully hear you. Otherwise, you'll be talking too fast for the peripheral to deal with you. Set the mode. By default, the mode is 0. Okay? So that may work for your peripheral. Yes?
You said like 16 megahertz wasn't an option. So what if your peripheral was running at 16 megahertz?
You can always talk slower, but you can't talk faster. For example, in this lecture, I am going slower than I would necessarily have to go to someone who's already had this lecture. But today I'm talking at a slower rate, even though I could talk faster. But I think if I were to talk faster, you guys would not retain as much information, right? So you are the limiting, not you particular, but you're the limiting factor. If you're the peripheral, you can only talk so fast. If somebody tries to talk to you faster, you're not going to get all of the data.
Oh, I see.
Okay, so you can talk to the peripheral. So if the peripheral has a maximum rate of 2 megahertz, you can talk to it at 1 megahertz and it'll work just fine.
Right,
Okay, you just can't talk to it at 4 megahertz. And yes?
Can it inherently understand slower things without having to be set to a slow pace?
Absolutely, because this is a synchronous protocol. Go back to the slide. It has a clock, and so this shift register is clocked by the master. Okay, and so both of them are clocked at the same time. This can get a little weird if this is like a cable that's 3 miles long or something, but for close things, you're all set, and that's not really an issue. You don't want to deal with clock skew, but so it is synchronous. So there doesn't need to be any a priori agreement that you're going to talk at 9600 baud or you're going to talk at this or that. The master really controls the show. It tells that guy when to shift. Okay. All right. Master operating mode. So we got to enable it. This is totally wrong. Totally wrong. Let's go back to that control and status register here. We want to turn on the SPE bit. The SPIE bit is the interrupt enable. So that's a small typo. I apologize for that. So we want to turn it on though. So we have to enable the peripheral with the SPE bit. So that's, let's do a pen here. The SP, no I, just SPE. Okay, now it's set up. That's our initialization procedure. Now we have to actually get data out. And all we have to do is actually quite painless. Anytime we put a byte in the data register, which is the last register, I haven't talked about it because it's just the data register. When you put a byte in that, it'll automatically start transmitting. Poof, because you're in master mode. So as soon as you put that byte in, it's going to start boop, 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 1 bit at a time, clocking things. We know that it's done when we have the spiff flag. When the spiff flag goes high, we know we're done. This is a polling type setup, not an interrupt type setup. So we poll. We sit there and we poll, and the data is finished transmitting once it's won. As soon as that flag goes high, we can then transmit the next byte. Now, here's the weird thing. We've just transmitted a byte out. But, much like Nietzsche, when you long transmit a byte out, a byte is long transmitted to you. No, nothing. Nietzsche. Stare long into the abyss. Abyss stares back at Baldur's Gate? No, nothing.
Sorry.
You should be. Okay, so as you send a byte out, you're also receiving a byte at the same time. There's no way around it. So you have to deal with that byte. And the weird thing is it's in the same register that you just put your data into. So you put a byte in, time passes, suddenly there's a new byte there. Okay, and you read that byte out to do something. So the note here is a little wordy, but it basically says if you're trying to read from a peripheral, say you might send a command, 1 byte out. It then knows that it has to send 2 bytes back to you. Forget what the peripheral is, but it's going to send 2 bytes. You need to send 2 dummy bytes because it, as a slave, can't initiate a transfer. The master has to make the transfer. So you'll frequently see lots of code that just sends, like OXFF, just sends a dummy byte out. Because sending a dummy byte out means you get a byte back in. Okay? So let's look at some code. This is code right out of your book, and it's pretty self-explanatory what's going on here. First off, up at the top, I've defined slave select to be 4, MOSI to be 5, sclock to be 7. I did not define MISO, because I only care about output right now. The other reason I didn't define MISO is because it's an input. It's automatically taken control of. Okay, I have to manually set these guys to be outputs. If I don't, even if I set up all of my control registers and my data registers, my status registers, it's not actually going to get out of the chip because I have to set them as outputs. So what do? I say, okay, turn on the MOSI, turn on the sclock, turn on the slave select. I'm not sure why I did 1 shifted left here and then bit value over there, but when I transcribed this, I transcribed all of these from the book into the M drive, so I may have taken a little creative license here. Furthermore, what do? I start by turning on the slave select bit, leaving it high because it is an active low signal. So by default, it's disabled. The peripheral is disabled because I wrote a 1 to the slave select bit. In terms of my setup, all I do is I enable it in master mode, and then I set up my clock divider. I'm not sure what I've set it up to in this example. Let's go look it up. I've set only SPR0. Where is it? Oh, it's inside of this shenanigans. So I set only SPR0, so that's a divide by 16. So if I'm running at 16 megahertz, I divide by 16. My clock frequency is going to be 1 megahertz. Okay. Oop, too far. 1 megahertz. Now, the rest of this is going to send G out over and over and over again. That's all it does. So the first thing I do is this line here. What does it mean when I AND equals tilde with a particular bit? You're setting it low. So the first thing I do in any transmission, any SPI transmission, is I activate the peripheral. I say, hey, hello, time to pay attention. Then I put data in. That automatically starts a transfer. So now, stuff's happening in the hardware. It's shifting bits out one at a time. Yes?
Is that the ASCII value of G?
It's the ASCII value of G.
Alright.
No, SPDR is the register.
Yeah.
That is the ASCII value of G.
Why are we setting that to G?
We're sending the character G out.
Oh, okay.
It's just random data. It could have been any byte. It could have been 1. It could have been 0. But we're sending G. Whatever. So now we're going to sit in this while loop. This is an empty while loop. We're going to sit in that for a while. So all we're doing here, though, is we're polling this spiff flag. This is saying, while it is 0, we've got that not here. While it is 0, do nothing. Finally, where am I? Need a laser pointer. Finally, this last line says, take whatever data we received, because we sent out a G, and when we sent out that G, we received a byte, put it on port A. Fine, we're just doing something with it. And finally, the last step in this process is we have to pull the chip select line back up high. That signals to our peripheral that we're done. One of the things I didn't really, hammer on here, in this diagram, everything starts when the chip select line goes low, and everything is finished when the chip select line goes high. Okay, so everything starts on that chip select line going low, and then it matters what the clock is doing. Okay, where are we? Master operating mode, examples. Okay, so the flags, though. The flag, that spiff flag, deserves a little bit of extra looking about here. And I brought this right out of the data sheet. And particularly, spiff is cleared by the hardware when you execute an interrupt handler. So that's nice. Interrupt vector will automatically clear it. In my code, though, just now, I didn't use interrupts. And yet somehow this is still going to work. And so I wanted to call your attention to the fact that the spiff flag can, it's cleared by first reading the status register with spiff being set and then accessing the data register, which is a weird way to clear flags if you think about it. You got to access 2 registers. What's up with that? Well, go back to this polling routine. You sit here and you poll this until it's 1. That means you access the status register while the spiff flag is 1. And then what are you doing? You're accessing the data register to receive data. So in the normal course of operations of your SPI device, you're already clearing the spiff flag, which is kind of pretty smart, I think. So this, by the way, is just a quick little function I wrote. The idea being it's going to send out some data, wait for it to finish transmitting, and return whatever it got back. We're going to talk about this a little later when I get to writing a library, because now that we're using other devices, it's time to start writing our own libraries. We've been dealing with all of the system libraries, io.h, programspace.h, okay? Those are built for the AVR processor. If we start talking to other stuff, we need to write our own libraries. So this is the start. All right. So if you're dealing slave mode, you set the mode to be whatever clock phase and polarity you want. Again, this is incorrect. I need to make a change here. This is supposed to be the SPE bit. Okay. Here's where things get interesting. It still looks like you're just putting data into the data register and polling the spiff flag. But now, when you put data into that data register, it doesn't automatically start sending. It goes into the data register, and then the hardware waits for the master to send something to you. So it's a little bit different. Instead of automatically starting to transmit, it sits there and waits for the master to transmit something to the slave. Okay, and then you receive that byte. All right. So SPI, not a lot going on there. Super powerful, used in lots of things, very fast, but not a whole lot going on. 2 shift registers. So we're going to start talking now about the lab. The lab is going to require you to use 7-segment displays. You've all used 7-segment displays. How many wires did you need to deal with those 7-segment displays? We had 4 7-segment displays. You had to wire it up. How many did you use? Like 15-ish, more than 10, less than 20. Okay. We're going to control, how many do you think you would need to control 8 7-segment displays? I mean, like math, you can handle this. 30-ish, maybe more like 16-ish, but 8 for the anodes, 8 for the cathodes, plus a ground, maybe something like that. But a bit. We're going to do it with 4. Sounds better? Much better. All right, we're going to do it through the use of a peripheral. I think you guys are pretty familiar with this. I'm not going to really spend a whole lot of time here. We're going to use this chip. This is the Max 7919 or the 7921. It can control up to 8 7-segment displays. It can even do brightness control. You can do super cool stuff with this. And you are going to be doing super cool stuff with this. Notice it has a chip select line. It's active low. Here, it's got a D in and a D out. So D in and D out are not standard SPI names, but I think that you can probably figure out what they should connect to if I tell you that this guy is the slave. So rename pin 1. If this is the slave device, what would you call that as its standard SPI name? SS is this guy, this chip select guy. MICE-O, that stands for master in, slave out. I think MOSI is probably more appropriate for the data in of the slave. And this would be slave out, so MICE-O here. MOSI, MICE-O. All right. So you'll see things like that. Different peripherals will call it different things, but you basically look which one is the input, which one is the output. It's the slave, so just assign it that way. Sometimes you'll see it just as S in, S out, or SI, SO. Don't be shocked at any kind of naming scheme. Just know that there's only 2 things in SPI, MICE-O and MOSI. And that's how you have to hook it up. So you'll see here on the right, we've got a bunch of segments, like decimal point, A, B, C, D, E, F, G. On the left, we have a bunch of digits, up to 8. So when we connect this guy up, very minimal components are needed. 1 set of anodes is set up for all 8 7-segment displays, and then you have 1 common cathode, which is how we have this set up. Over here, this is a 3-wire interface, only MOSI rather, only master out. There's no data coming back to you. Slave select, chip select, and plug. Ground obviously is set up. And then this current set resistor sets the brightness to all the LEDs using a current mirror to set up the brightness, or the maximum brightness, I should say, because we can dim the brightness using internal pulse width modulation. So this actually can handle PWM signals. I'm eventually going to transition into the data sheet for this, but I want to go over the basics of how this all works before we go to the data sheet. So the way we communicate with the 7919 or 7921 is 2 bytes at a time. So you'll see here the chip select line goes low, 2 bytes are transmitted, and then the chip select line goes high, which at first glance might present an interesting problem because we have an 8-bit processor. We only handle 8-bit transfers. But it's not really a problem. We just do 2 8-bit transfers to make 16 bits. If we had a 24-bit communication protocol, we'd do 3 bytes worth of data. Furthermore, these bytes are broken down into smaller chunks. You have a command byte and a data byte. The command is one of 16 commands, and then the data is related to that command. which, by the way, just go back just a little bit to that code we had earlier. This code doesn't affect the chip select bit. Okay, so as a result, we could call this function SPI send twice, and all we'd have to do is add in a little function above for setting the chip select low, and then a function after those two calls to set the chip select high. Okay, just think about all of these things, how they're going to operate together. So, second byte of the 2-byte packet is called the data packet. Here are the commands. The commands aren't all that interesting. We have no command, no operation, do nothing. Then we have 8 commands, each of which sets a particular digit's value. You can set it, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The next command is called decoding mode. Remember those lookup tables you guys had to create for 7-segment displays? Well, this chip has that built in. Almost. It has 0 through 9 built in. And then for whatever reason, the only other thing it can do, instead of doing A, B, C, D, E, F, it can spell help with a dash. And I have no idea why. They call it the code B font. I'll show it to you in the data sheet. They call it the code B font. There is no code A font. I've looked. If somebody is watching this like years from now or even days from now and knows what the other code fonts are, I would love to know. Leave a note in the comments down below. Then we've got, the next command is set intensity of light, which is actually allows us to dim it, dim the whole display. It uses pulse width modulation. I don't remember what the PWM frequency is, but you can effectively make it dimmer or brighter. Okay, what do we have? Intensity of light. Okay, last couple. We've got a display test. I'm going from bottom to top now. Display test just turns everything on. Just make sure that your LEDs are all working. Turn on and off basically turns off the display or on the display. Last is scan limit, and this one's kind of the most difficult to explain because it is using time division multiplexing to drive these things. So in my time division multiplexing code, one of the things I had was a digit count. I knew which digit I was going to display next. And when I got in, I was doing 4 digits, I'd go 0, 1, 2, 3, and reset back to 0. That's really what the scan limit is doing. It's saying what my maximum value is. So by default, my maximum is 0. It'll only time division multiplex that first digit. If you set it to 1, it'll do digits 0 and 1. If you set it to 2, and if you set it to 8, if you set it to 7, it'll do 0, 1, 2, 3, 5, 6, 7. It'll do all of them. For your lab, yeah, you want to set this to 7. So what does that mean? When we send a command, for example, the scan byte command, we want to send the command of a scan is B. So you want to send a 0B in the command byte, and then you want to send, for example, a 7 to say, or maybe it's bitmasked. It might be bitmasked, which scan modes you want to use. Okay, so those are the commands that you can use. That's all 16 commands. It's really not that interesting. Most of it is just how to easily set up your bytes. Okay. Here's the decoding. So decoding can be done on a digit by digit basis. Either you can use their built-in code B font, and that means that if you put a 0 in, it'll display the character 0. Or you can manually control each bit of the LED, each bit of the segments. So if you choose to not use decoding mode, which you might want to do, you can set it up like this. Bit 7 is the decimal point, bit 6 is A, bit 0 is G. That might be opposite from how you've created your lookup table in the past. I don't recall. Usually I think we put G right next to decimal point. So you may have to rework that lookup table a little bit for your lab. Okay? That's if your decoding mode is off. If decoding mode is on, sending this command right here, this command will make the digit 5 display on a 7-segment display because that's the binary representation of 5. Okay. Furthermore, this command, by the way, this command says set digit 3 to be a 5. So if you wanted to create a function that would write a whole 8-bit number or 8-digit number out, you could do that by sending 8 different packets with a different command byte each time. So when we set this up to talk to this 7221 or the 7219, we've got to initialize the SPI. It's a master mode. We've got to enable or disable the decoding mode, set the scan limit because the default is 0. And we've got to set the intensity. We probably want brightest. Turn on the display. That's a third command that has to go across the SPI bus. And finally, set the value of each digit. Okay, so how do we even approach a problem like this? I haven't actually told you what the lab is yet. It involves basically an alarm clock. You're going to do month, day, hour, minute, each groups of 2 like that. But we want to write a general library for this 7221 chip. Did I bring one with me? I don't think so. We want to write a library of code so that we can make our lives easier. And why would we create a library? There's actually tons of reasons to write a library. First is to abstract away any low-level details. Okay, we don't want to remember which I/O pins things are. We just want to say go, enable. And that will allow us to code what we want to do, not code how we want to do it. We write the library once, and then we just use that library from then on. It promotes self-documenting code. If you have a function that says set digit 0, that's pretty clear what you're going to be doing then, if you write it correctly, right? If you write it wrong, it's worse than useless. The other reason we write libraries is for portability. If you actually look at the AVR/IO header file, that's a file we've used in every C program since we started talking about C. You're actually going to see, let me pull it up. Oh, you can't see that. Okay, here it is. Here's the AVR/IO.h. Now, I told you way back when that it defined all of the ports, all of those special purpose registers, defined all of that stuff. Well, let's look for that, huh? Comments. Okay. Looks like we've got some defines here, some more defines here, some more defines here. And then nothing. Where are all my ports? Where's all this stuff? As a former colleague of mine used to say, where's the beef? Well, the beef is actually, the good stuff, is inside of other header files. So I'm going to actually go now, I'm going to open up one of these other header files. AVR IOM32 M328P.h. Where is it? There it is. Here's IOM328P.h. This has all the stuff that I'd expect to see. There's pin B, DDR-B, port C. We keep going. We've got our interrupt masks, general purpose registers, EEPROM. There's our timers. We can even go down a little further, and we should see. I did just see it. Okay. Lots of good stuff. All the stuff that we've come to expect. More timers, analog to digital converters, it's all here. So how do we get to here? Well, as part of our project creation, we have to select what processor we're targeting, right? Well, this file, no, not this file, this file basically says if a particular processor has been defined, so this, for example, is the ATmega 88. It's a smaller cousin of the 328P. If that's defined, then we define this particular header file. So if you're writing a really robust library, you can have stuff like this inside your library, and that'll abstract away which processor you're using. So one library can work for multiple devices. In fact, you don't even have to be limited to the AVR toolchain. You could work with, with an ARM processor, and that would be pretty cool too. So it doesn't really matter what you use. Let's go back here now to this. Record. See all slides. And finally, modularity that's implied in making a library or a module. You get to take this with you when you're done. You don't tailor it to a particular application. You make it as general as possible. So then you can take that module, you can make it more specific later if you want, and that almost like inheritance in C++, but let's not go there. Let's deal with strict C for now. Okay. So first step in creating a library, we're going to go through these steps, is low-level functions. The idea here is that you don't see any I/O registers after these functions. You should be able to do everything you want to do just with low-level functions. So here are my candidates for low-level functions. I'm trying to write a library for the MAX 7221. So it's an SPI device, so I've got three functions. One is initialize SPI. That takes care of writing to my prescaler bits, my polarity bits, all that good stuff. My second is an SPI send function. I've actually already written that on a previous slide. It was dead simple. Puts data out and returns whatever was received. Okay, for the MAX 7221, we don't receive anything because there's no data coming out. And finally, this may seem like the weirdest one. SPI set chip select. It's really easy to set a bit low. It's super easy. We did it just a few seconds ago. Right here. That's how we set something high. Oh. Where did it go? Port B, that's how we set something high. Let's go to my laser pointer. That's how we set a bit high. That's how we set a bit low. Why wouldn't we just put those lines in? Because the goal of low-level functions is to eliminate anything that might be purple here, right? Eliminate port B, eliminate the need to know what the slave select bit is. We just want to say enable the chip select or disable the chip select. Or we could say set chip select high, set chip select low. That's all we want to handle. Go back here. So if you define your low-level functions correctly, you never have to talk to the hardware again. You can abstract that out. So now you have these low-level functions that will talk to the hardware. The nice thing about having these low-level functions is if you decide to move to a different processor or to move to a different architecture altogether, you want to go from, say, this processor to an ARM processor or to one of Motorola's HC12 or HC09 processors. You want to move to an Intel processor. You want to move to some really weird version of a processor, like whatever's inside the ECE263 or beyond. It doesn't matter. You just rewrite those three functions, and everything else still works. All of your higher level functions that rely on these low level functions will work as long as these work correctly. And these are pretty easy to check too. It's easy to check if the chip select function works. You just run it, see what happens to the pin. It's easy to check your SPI send function, hook it up to something, and see if the bits come out. Yes?
So how do we know, though, if we're going with a different process, how do we know that it has the same, like SPI or MISO bit?
Well, first, SPI is a standard. So you know that.
Right.
So you know that. But maybe you don't, right? Maybe you don't. Maybe you don't even have an SPI hardware peripheral. What would you have to do? Well, you could rewrite your SPI send function to bit bang it out. You know, send the data out, manually toggle a pin low, manually toggle a pin high, send out the next bit, and over and over and over. So you could manually do it. You could write it yourself. You don't have to rely on the hardware now. It doesn't really matter because you've abstracted away. All you know is when you call SPI send, it pops 8 bits out and returns 8 bits to you.
This goes back to a while ago, but can you explain the difference between firmware, between software
Start that one again. You want me to explain the difference between firmware in software and hardware?
Between the three, because I know software is just code and hardware is machine. So
okay, so all firmware is software, but not all software is firmware. Okay. Hardware is hardware. Firmware runs directly on the hardware. Software runs on more general purpose hardware. That's a little bit beyond the scope of the course. We can talk about that maybe in my office hours, okay? But you for now just remember that all firmware is software.
would an example then be like kernel interrupt?
No. So firmware defines how the software gets run. Office hours. Let's get these low-level functions out of the way because this is going to help you out. I'm going to now switch over to duplicate mode, and then I'm probably going to have to change my camera settings here. You can see that. Turn that off. Turn that on. And we're nice and trippy. Okay, get rid of that. So this, by the way, was the same code I used before. This, by the way, is one way of doing parts of a library. This is specifically targeted towards the ATmega 32. You may remember that it was 4, 5, 6, 7 on that. If I wanted to change this code to work with the ATmega 328P, all I'd have to do is change those 3 lines to address the fact that on the 328P, MOSI is B3. So I could change that to 3. I could even, actually, let's do this. Let's, like that, define MOSI as 3, define SCK as, what's SCK? 5, and finally define slave select as 2. Okay, so here's first approach at a library. Let me make that a little bigger. I have comments, right? So this is the comment ATmega 328P, and then I could put a comment here ATmega 32. So now, depending on what I want to target, I can uncomment these things. That's not great. We can modify this a little bit using some compiler directives. Okay, first I'm going to just cheat by going back here, 328P. Okay, I'm going to steal this piece right here. Okay, and I'm going to say now, instead of commenting one out or the other, I'm going to say pound if defined 328P or 328, define it that way. And then I'm going to look for the ATmega 32. There it is. So I'm just grabbing these out. You can always look these up in a table somewhere. Else, if it's defined as the 32, do that. Else, and here's where I have a little bit of leeway. So if you look at the end of this, if you go through all these things and it says else, what do? We can say warning. That's a compiler directive, device not defined. Or you can say error, and it won't even compile, which is something interesting. So this is the start of a multi-processor library. We define a few things based on where we know these things are. It's mind-numbingly boring to go through all the data sheets for all the things. You would start your library out with the things you think you might be targeting, and then add them in as time goes on. Yeah?
If it reaches that warning, then doesn't just stop the program, what would it continue as?
Well, it would actually not be defined as anything. Okay? It would cause an error the first time you used it here. So you'd get a warning, device type not defined, and then you'd get an error, MOSI undefined. All right, that's how it would work. You could just make it cause an error here if you wanted. So you could append this many, many times if you so desired.
Why not just include the file that you just copied,
Because that is dealing with the I/O stuff. That I/O stuff, if you look at the I/O 328p bit, I don't think anywhere. I'll try finding MOSI. No, let's search for SPI. So here's the SPI stuff. All right, the SPI right here that's the SPI peripheral. That's all the bit names, okay, and so forth. If I look for port B, really? Oh, no, I don't want to look in this selected text. I want to look in the whole current document. Here's the port B bits defined, but nowhere in here does it define in the IO 328p header file what the alternative bits do. Okay, it doesn't define S clock as being bit B5. Okay, so that's a piece of this. All right. Now, what I wanted to do, though, was low-level functions. This is sort of before low-level functions. This is just hardware. So those candidates that I mentioned, init, SPI, actually, let's try to keep a common naming convention. SPI init, SPI send, and SPI chip select. We have to define those, so that's just the names of them, not what arguments they take. Probably a init, like most things, will be void, because it's just going to do its job. And what would we be doing in SPI init? Well, we'd have to be master mode. We'd have to set up our clock divider. Okay. Probably not doing interrupts. Okay, but so master mode, how do we do master mode? Well, now we're going to be going back and forth between data sheets all over the place. Okay, so my status register only has the SPIF flag and the SPI2X bit. My control register has the enable bit, has my clock and phase, my clock phase and my so forth. So let's actually grab most of that from a previous example here. Where did my example go? There it is. Oh, it's up top or down below. So when I set this up, things that I want to make sure I do, I want to be enabled, I want to be in master mode, and I'm going to choose just a different clock divider just to be, interesting here. Here's my clock divider. Let's set up it to run as fast as we can. Or can we? Ooh, can we run as fast as we can? Depends on what we're talking to. We need to know what we're talking to. We're talking to the MAX 7221. Well, look, it's the data sheet for the MAX 7221. Well, right there in the features, it tells us, boom, it has a 10 megahertz serial interface. That means the fastest it can talk is 10 megahertz. So our system clock on our dev board is what? 16 divided by 2 is 8 greater than or less than 10? Less than. So we're fine. We can do that. So we're going to run in master mode. We're going to do a divide by 2. Our clock is going to be divided by 2. And we need to know our polarity and phase, SPI mode. So, all right, we're going to have to go back to the data sheet. We're going to have to look. Let's see. Does it say it in the features? Does it say it in the features? Segment control, brightness control, slew rate, SPI. No. Question.
Is there a performance trade-off when we're talking something that could talk faster, but we can only talk?
So with this, not that much. But consider an analog to digital converter. Let's say that it's a stupidly fast. Let's just throw out a completely bogus number. 26 gigasamples per second. Okay, that's like ridiculous. 26 gigasamples a second. You can only transmit at 10 megahertz. So how are you going to get 26 billion samples out if you can only talk at 10 million bits per second? Okay, so in certain cases, you want to run as fast as you can because you want to get data out as fast as you can. So if you talk slower, you're going to start missing samples.
So it is a bottleneck when it comes to different scales.
Yeah, it's the communication bottleneck. So you want to usually talk as close to the peripheral's top speed as you can. The other trade-off there is you're sitting there polling, right? That means that you're waiting there doing nothing, right? So you want to deal with that. So I've got to start looking through this data sheet, though, for that polarity and phase information. Typically, what I do the first time I look at a data sheet is I just kind of do one of these, looking through and seeing, okay, I've got tables, I've got some text, I've got maybe some recommended diagrams. Okay, I've got package information. So I'm looking right now for things like timing diagrams. And I'm just scrolling through, just kind of hoping that, ooh, okay, here's my first timing diagram. And this gives me all the information I need to know to find out my clock and phase. Because remember, clock and phase is just about when you read and when your data changes. I can clearly see here, where's my mouse, that the data is stable on the rising edge, and it changes on the falling edge. All of these other things, that's like various timing information, but I already have the timing information. I care about 10 megahertz. I can run this at a max of 10 megahertz. Okay, so I know that I need to read on the rising edge, change on the falling edge. That can be SPI mode 0. SPI mode is 0, 0. Okay, so now I can begin to start writing up my initialization because I've looked through all this stuff. So let's, I want to go back to the data sheet for the 328P and look at this register. So I want to do this mode. That requires SPR1 and SPR0 to be both 0 and SPI2X to be a 1. So what I'm going to do is I'm going to say 0B00 shifted left by SPR0. That will in turn put 2 zeros here. For polarity and phase, I want both to be 0. So I'm going to say, maybe I won't say, let's try it again. ORed with underscore BV C Paul, ORed with underscore BV C, I think that's how it's set up. A quick check of the library will tell me if that's correct. It'll compile or it won't, but I'm pretty sure that that's exactly how it's set up. CPHA. So that sets my polarity and phase. That actually sets it to 1, 1. So that's mode 1, 1. But 1, 1, remember from before, is actually the same thing as 0, 0. They both read on the rising edge and change on the falling edge. I am in master mode. I am enabled. What else is in here? Ooh, my data order. Do I do the most significant bit first or the least significant? To handle that, I need to go back and I need to look. I'm doing the most significant first and then the least significant last. So if I look at the data sheet, I keep going to a different thing. If I go to the data sheet now, if the DORD is written to 1, the least significant bit is transmitted first. If a 0 is written, that means the most significant. So we want a 0 here. So I'm just going to say 0 shifted left by DORD. All this is just going back and forth between data sheets, checking each bit until I've set all of them. Yes? I do need an OR right here.
Then also, so I thought we were trying to make the SPI init function as general as possible, and this is catering to the chip.
Yeah, so I'm picking and choosing when to pay attention to that advice. My send function is going to be as general as possible. What you could do if you were trying to make a truly generalized function is you could do this. uint 8 underscore t Okay, you could pass in arguments, and then based on these arguments, you would set stuff. That's probably a little bit better, okay? But for the sake of time, I want to get you up and running on this, Chip.
Okay.
So this is probably the least generic of all of the things. But if you started doing a setup like this, you could basically have one argument for each bit, and then you'd have another function that would call SPI init with particular arguments. That's a valid point to make, though, is we are making this a little bit tailored. But this could work for many different things. Anything that can speak at least 8 megahertz uses mode 0 or 3 and takes most significant bit first. Okay. So that handles that. The only thing we have left to do is the status register. Okay. The status register needs that 2x bit. And what's that called? SPI 2x. Okay. So there's our first library function. I know we're out of time. Let's do this one real quick. All right. This one's pretty darn quick. Because this one, I'm going to actually say, I am going to give it an argument. Okay. And this could be written a couple of different ways. I'm going to do it the lazy way. If val port b or equals underscore bv ss, else port b and equals tilde underscore bv ss. That's it. It may seem silly to make a function that does that. It's so trivial as to almost be nonsensical. But what it allows you to do is you never have to talk to port B or any of the SPI peripherals ever again. And actually with that, we have now handled all of those low-level functions because we've already seen the SPI send function, wherever it was, back here somewhere. There it is. Okay, that's it. That's the whole thing. So with these low-level functions, next class, we're going to dive into the Max 7219 chip and continue building up a library, and we'll talk more about the lab.